Okay, welcome back. Just a second. So what we are doing is that we are talking about power law degree distributions, and we want to estimate the size of the largest cut in the network using the upper natural cutoff. And as I said in the previous video, we will first try to do that for a random graph. We said that a random graph has a Poisson degree distribution. However, we will now make these computations for an exponential distribution that has similar properties, and computations are much easier. So let's do that. So an exponential degree distribution will be some parameter gamma times the exponential function of some parameter lambda times the exponential function of lambda times k sub mean, and times the exponential function of minus lambda times k. So in order to compute the upper natural cutoff, the size of the largest k that we can expect, we will compute the integral of this exponential distribution from k max to infinity, and we will demand that this integral equals to 1 over n. And this is done here on the slide, and I will not copy this on the blackboard. So we take the integral from k max to infinity, we plug in the exponential distribution and compute its indefinite integral and evaluate it at the upper and lower bound. Again, since this term here is actually downstairs because of the minus, we get 0 when we plug in the infinity. So we only have to evaluate the indefinite integral at k sub max, and this is the final result that we get. Just a second. So we said that this must be equal to n to the power of minus 1. So now if we take the logarithms of both sides and isolate the k sub max, what we get is that the maximum degree equals the minimum degree plus the logarithm of the number of nodes divided by lambda. So the main thing here to see is that the size of the largest hub scales logarithmically with the size of the network. K sub mean will be some small number, lambda is also some parameters, so how k sub max scale is basically the logarithm of n. So it will scale very slowly with n. Even for large values of n, we do not expect to get very high degrees. However, on the other hand, if we do the same computations for a scale-free network that has a power law degree distribution that we have already derived, we again compute the integral between k sub max and infinity. So this is simply the indefinite integral of some polynomial. We again evaluate it at upper and lower bound. Again, since gamma is has to be strictly larger than 1, this term is actually downstairs. So when we plug in the infinity, we get 0. So we only have to evaluate it at the lower bound, which is k sub max, and this is the final result that we get, and this has to be equal to n to the power of minus 1. Now, again, to isolate k sub max, we take we set both sides of the equation to the power of gamma minus 1 and isolate k sub max, and what do we get is that k sub max equals k sub min times n to the power of 1 divided by gamma minus 1. Now, this exponent will of course depend on gamma. However, if we assume that the gamma is something between 2 or 3, or for instance if we assume that gamma equals to 2, what do we get is n to the power of 1. So the largest degree in a scale-free network will scale with the size of the network. Or maybe when gamma is free, it will scale with the square root of network. But in any case, it will be some polynomial of n. So when n gets super large, also k max will get super large. To more clearly see the difference between these two functions, here is a plot on again double logarithmic axis. And in the case of a random network or a network with exponential degree distribution, the k-sub max will scale as a logarithm of n, so it will scale very slowly. However, in the case of a scale-free network with a power law degree distribution, k-sub max will scale as some polynomial of n, so it will scale much quicker than in the case of a random network. So you can visually see that for network of the size of 10 to the power of 10, for instance, the expected maximum degree in a random network is around 10, whereas in the case of a scale-free network is something around a million, for instance. So there is, of course, a huge difference. And this here, this gray line is just showing you the theoretically possible maximum degree in the network, where you have a node that connects to every other node, which will be n minus 1. To again look at an example, what is the size of the largest hub, or what is the maximum degree in the snapshot of World Wide Web from '99 that had around 300,000 nodes. The exact number is 325,000 and some change. And let's first assume that this lambda parameter of the exponential function equals to 1, and let's set this k-min parameter to 1. So saying that there exists at least one node that has degree 1. What do we get is that the estimated size of the largest hub is around 14. So the largest degree that we will get is around 14. However, if we do the same computation for a scale-free network with the same size, and let's take the estimate of gamma that was estimated in '99, and so we plug this in here, and again assume that k-min equals to 1. What do we get is that the maximum degree in the network is around 100,000. So you can see that there is 4 orders of magnitude difference between the largest hub in a random graph and a scale-free network, although the network is still not that large. So indeed, the size of the largest hub in real networks is a very large number. Okay, to move on. This slide here is trying. The main point of this slide here is to explain why do we call power law a scale-free distribution. It has to do with the fact that it lacks scale. There is no characteristic scale in the case of a power law, in contrast to, for instance, a random graph with Poisson distribution. And for that, we will use the moments of degree distributions, let me say a couple of things about that. So I'm not sure whether you talked about moments of probability distributions in any probability or statistic class, but it's nothing fancy actually. So moments of the probability distribution are some numbers that characterize the distribution. The first moment is simply the average. So in our case, when we are dealing with the degrees, the first moment is simply the average degree. Now, the second moment is the average of the squares of the degrees. So expected value of the square. So the second moment will be the expected value of k squared. And finally, the third moment would then be the expected value of the k to the power of 3, and so on and so forth. On the slide, I will denote different moments with different values of x, where x will tell me this exponent. So for the first moment, x will equal 1, then x will equal 2, and x will equal 3 for the third moment. As we will see, we are mostly will be interested in these first two moments. Now, why would that be interesting? The average is simply the characteristic value for the distribution. Now, next, the second moment tells you something about the spread of the distribution, where the distribution is like very narrow, or is it very wide, like spread to both sides. Basically, this second moment determines the standard deviation of the values of x. And why is this so? According to the standard formula, the standard deviation of k to the power of 2, which is basically the variance, will equal the second moment minus the square of the first moment. You're probably more familiar with this function that to write the variance of some random variable is the expected value of the square minus the square of the expected values. So going back to the second moment, you can see that the standard deviation is basically determined by the second moment minus the square of the first moment will usually be some modest number. So basically the second moment tells you something about the spread of the distribution. Now, if you're interested, what does the third moment tells us? It tells us about the skewedness of the distribution. Whether the distribution is either skewed to the left or skewed to the right. So there is more mass of the distribution on the right side or on the left side. Okay, let's go back to the slide and then we'll again move back to the blackboard. So we are interested in computing the moments of the power law degree distribution, and with x I will denote either the first, second or third moment. And as I already said, the first moment is just the average, the second moment determines the spread because it's connected to the standard deviation or the variance, and the third moment determines the skewness, whether you're skewed to the left or skewed to the right. Now, to compute the values of different moments for a power law, continuous power law degree distribution, we take the expected value of x moment. Here is the exact computation using the theoretical power law. We are again approximating this with an analytically convenient continuous power law approximation, and what we're simply doing is multiplying k to the power of x for all different values of x times the probability for all different values of k times the probability that we will see such a k in our network. And the upper and lower bound will now be set from k min to k max, because we already computed k max on the previous slide. Now you can plug in the values for the power law distribution here, compute this integral, which is just like you're just integrating a polynomial, and you will get a certain function, and this here on the right hand side is showing you how this function, how these values scale. There are some constants here in the front or at the back that we are not really interested at this moment. So let me copy this on the blackboard. So what did we get is that the x moment scales like k sub max to the power of x minus gamma plus 1, then minus k sub min to the same power divided by x minus gamma plus 1. Okay, I will now make the camera larger. When we are now talking about these moments, we are not that interested in the exact values, but how these values scale where n goes to infinity. Meaning, when n goes to infinity, does this moment go to some finite value, they converge to some value, or they go to infinity, which will be saying that the moment diverges. So where when n goes to infinity, also the moment goes to infinity. Now let's see which moments are actually diverging and which are finite. Now looking at this fraction here. Firstly, x minus gamma plus 1. So x is some number 1, 2, 3. Gamma is some number usually between 2 and 3 plus 1. So basically here at the bottom, this is some number, some constant that does not depend on n, so the size of the network. So if we're just talking about the scaling where n goes to infinity, then we can basically forget about this part. So we are only looking upstairs now. Now look at the term at the right hand side. This is k min to some power, which is again some number. Now k min in most networks you will have a node with degree 1 or maybe node with degree 2 or something like that. So this k min will actually be a very small number and it will not scale with n. Even when you scale to millions or billions or trillions of nodes, you still expect to have at least one node with degree 1. So this will also be some modest number that will not scale with n. So just for the scaling of these moments, where they are finite or not, we can also forget about this part. So we are only left with k sub max to the power of x minus gamma plus 1. Now here, we cannot just cross this value. Why? Because on the previous slide, we have shown that k sub max in the case of a power law scales with n. When n goes to infinity, also k sub max goes to infinity. And infinity to some power will also go to infinity, meaning that the moment will diverge. Now, the important thing to notice here is that now I have written this term upstairs. But it really depends whether this is actually upstairs or is this downstairs. It depends on this exponent here. So if this exponent is positive, then when n goes to infinity, k max goes to infinity and the entire term goes to infinity and the moment is diverging. However, if this exponent is actually negative, meaning that this entire term is downstairs, then when n goes to infinity, k max goes to infinity, but since this is downstairs, the entire fraction will go to 0 or to some finite value. So it all comes down to which moment will be diverging and which moment will be not, whether this term here is positive or not, whether it is upstairs or whether it is downstairs. So we are just interested k minus gamma plus 1 must be upstairs in order for the moment to must be downstairs in order for this moment to be finite. So this must be smaller or equal to 0. So let's write this, let's isolate x, and we get x must be smaller or equal gamma minus 1. And this is our final result. So all x's, all moments that correspond to some x that is smaller than gamma minus 1 will be finite, whereas all x's that are larger than gamma minus 1 will be diverging. So they will go to infinity when n goes to infinity. Now the question is, which moments are now finite and which are diverging? Of course, depends on this value of gamma. I told you that in most networks, the gamma is somewhere between 2 and 3. And let's set the gamma to equal to, let's say, 2.5. Then what do we get is that the finite moments are those where x is smaller than 1.5, and the diverging moments are those where x is larger than 1.5. Meaning that for gamma 2.5, the first moment is finite, meaning the average is finite. However, the second moment is already diverging, and also the third moment, the fourth moment, and so on. And this basically comes down to the fact that why we call these distributions scale-free. So here the second bullet is exactly what I have drawn on the blackboard. So for scale-free networks with gamma smaller than 3, so with gamma for instance between 2 and 3, we say that they lack scale. Often you write some variable as its average plus minus its standard deviation. And we have shown for gamma smaller than 3, then we would write that k is the average plus minus the infinity, because the second moment is diverging, the standard deviation is diverging, so there is no characteristic scale. Although you can always compute the average, but then the things are so widely spread there that most of the nodes do not have degree close to the average. Whereas this is in contrast to random graphs that have scale, as you can write that k equals the average degree plus and minus the standard deviation of a degree distribution of a random graph. And you can look to Wikipedia and you will simply see that this is the standard deviation of the Poisson distribution. So for that reason, because the second moment, the second part of the equation is finite, we say that random graphs have scale. Maybe to further understand that is, since power laws do not have scale, there is no characteristic value of the degree for nodes in a network. The degrees are all over the place because the standard deviation is diverging. It goes to infinity when n goes to infinity. And this is the main reason why we call scale-free networks, why we call networks with power law degree distribution scale-free, because they lack characteristic scale. I don't know whether I mentioned this in any of the previous lectures, but regarding the Slutinian terminology, scale-free networks are called Brez-Lestvicna umrežja, and power law function, it's called potenčni zakon, potenčna funkcija, potenčni zakon. Okay. Let us move on to the next slide that is just trying to show these results in what we have just derived for some real networks. On the left-hand side, you can see the degree distribution of some real networks, and on the right-hand side, you can see how the degrees spread for different real networks. So we are plotting their standard deviation, which is basically just the square root of the second moment. And we are plotting on the horizontal axis, we have the average degree, and on vertical axis, we have the standard deviation. And we shown on the previous slide that the standard deviation will scale as a square root of the average degree in the case of a random graph. However, you can see that in most real networks, the standard deviation is much higher than what you would expect in a random graph, so they really do not have a scale. The values are, of course, not infinite because the networks are finite. I mean, we cannot send n to infinity. However, we do expect that when these networks are going to get larger and larger and larger, also the standard deviation will get larger and larger and larger, will be diverging. Okay, so let's also relate scale-free networks with small world networks. So if I take a network that is scale-free, so that it has a power law degree distribution, how long will the distances be in such a network, or in some model that will generate a network with that kind of degree distribution? So, firstly, for a random graph, we've shown that the average distance scale as a logarithm of n, and I'm here saying that these networks are then small world, but with these quotations, because we are only here saying that the distances are short. However, the clustering is also short, and the proper small world networks must also have high clustering. However, in Barabashi's book, he's calling networks with short distances already to be small world. I'm using these quotations. For scale-free networks with gamma larger than 3, you can also show that the distances will scale logarithmically with the size of the n. However, in scale-free networks with gamma between 2 and 3, actually the distances scale as a log of n, and this is sometimes called ultra small world networks. So distances are even shorter than what you would expect in a random graph. And this plot is showing you these functions of average distance for different sizes of the network. So here is the scaling for a random graph, so log n. Notice that I'm using semi-logarithmic scales. So this scale is linear, this one is logarithmic, and in this case a logarithm will look like a straight line. So this is what we get for a random graph, and for instance here is what we get for a scale-free network with gamma between 2 and 3, and notice that the distances are even much shorter than what you would expect in a random graph. However, you must go to networks large enough to clearly see the differences. For instance, for very small networks, the differences between this log n and log n is not actually clearly visible. Okay, so we have only 3 more slides, and maybe the next one is the most important one that basically summarizes everything that was said on the previous slides. So here we are seeing different values of this parameter gamma between 1 and 2, gamma between 2 and 3, and gamma between 3 larger than 3. As I said, most real networks have gamma between 2 and 3. We have shown that in the case of gamma between 1 and 2, both first and the second moment are diverging. In the case of gamma between 2 and 3, the average is finite, however the standard deviation is diverging. And in the case of gamma larger than 3, both of these two moments are finite, so that the degree distribution has a scale in contrast to this scale-free regime. We have shown or said that the distances in this scale-free regime are log n, so something that you will call ultra small world network, whereas in the case of gamma larger than 3, the distances scale as the logarithm of n, something that we already see in the case of a random graph. And here at the very bottom, you also have this estimate that we have computed. How does the largest hub, how does the degree of the largest hub scale in these networks? Let me maybe, so basically these are all the results that we have derived. This left side, it has here anomalous regime, no large network can exist here. Why is that the case? That we have shown that gamma must be larger than 1 so that you can integrate that function, otherwise it's, such network cannot exist. But it turns out that also gamma must be larger than, larger or equal to 2. And why is that? If you plug some value between 1 and 2, let's say 1/2, into this formula, you get 1/2 minus 1, so it's 0.5. 1 divided by 0.5 is 2, so K must scale as the square of n, meaning that the largest degree scales as a square of the size of the network, which is of course impossible. You can only connect to at most n minus 1 nodes. And also, you can check, you can generate power law distributions with exponent between 1 and 2, sample the values out of that, which will be your degrees, and then try to construct a network with that kind of degree sequence. So something that we already called when we talked about configuration model, we said that that kind of sequence is then graphical, so that it's actually possible to construct a graph. It turns out that there is no graphical degree sequence for gamma smaller than 2. So this is why you don't expect, at least that's important, in a simple graph, you cannot have a network with gamma between 1 and 2. Now, finally, this right-hand side is telling you that when gamma is larger than 3, the network, the real network or the scale-free network, will be indistinguishable from a random network. And why is that the case? Look at this formula here, which is basically, let me go back, which is this formula here that we have derived, just that you isolate n. Now, in order to estimate properly this gamma exponent of some degree distribution, you will usually you would demand that the values from which you are estimating the gamma scale at least 3 orders of magnitude. So for instance, that the values of the degree are, for instance, between 10 and 10,000. This will be 3 orders of magnitude. So here on the slide, this is basically K max divided by K min, and I need this to be at least 3 order of magnitude, so that value will be 10 to the power of 3. Now imagine that you have a network with some very large gamma, let's say gamma 6 for instance. Then the formula will say that 10 to the power of 3 should be risen to the power of 6 minus 1, which is 5, so I get 10 to the power of 15. Meaning that in order to be able to estimate gamma when gamma equals to 6, you need a network with at least 10 to the power of 15 nodes. And there is no such network. We said that the largest network is the World Wide Web, which is of the order of 10 to the 12. So what I'm trying to say that there might be scale-free networks with gamma much larger than 3. There are simply no networks that large enough that we could, in a statistically relevant way, be able to estimate that. Okay, so 2 more slides. Here is just a list of different distributions that you often see in the network science literature. Here we have this discrete power law, continuous power law. Notice that many other distributions will also be scale-free, will also look roughly like a power law, meaning that the tail goes down polynomially fast. One such example would be, for instance, log normal distribution, which looks like a normal distribution, but instead of parameter x, you take the logarithm of x. And then this exponential function and this logarithm roughly cancel out. So what you will get is a polynomial scaling in x. In contrast to a normal, to the classical normal distribution, where the scaling here will be exponential. Just the very last slide, how these scale-free networks or networks with a power law degree distribution have been reported in the literature. So the first paper reporting a network with a power law degree distribution will be in 1965, where Delek de Sola Price was looking at networks of citations between scientific papers and already showed that the in-degree distribution follows a power law. Then usually when we talk about scale-free networks, people cite a paper of Reka Albert and Laszlo Barabashi, where they showed in different real-world networks that the degree distribution really follows a power law, and they also come up with a simple model that explains their so-called preferential attachment model. Actually, at the same year, there was a conference paper on showing that internet topology, internet map, also has a power law degree distribution, and this was published by the three Falustos brothers, which are all computer scientists or professors and so on. And here is also a timeline how people realize that also other real networks have a power law degree distribution. Here is, for instance, email network, metabolic networks, in the case of Twitter in 2010, Facebook in 2011, and so on. So nowadays, we believe that most networks are scale-free, meaning that they have a degree distribution that can be well approximated by power law. However, you should still realize that some real networks will not have such degree distribution if we move to the very first slide, for instance. So this is it for these lectures. Thank you for listening.